Okay, let's unpack this. We live in the age of, well, the trillion parameter model, right?
Right.
If you want to solve a hard problem, the standard thinking is, you throw a massive large language model at it. Think GPT, think Gemini.
Scale is king. Or simply
Exactly.
not.
Scale is everything. But what if I told you there's a model out there with less than 0.01% of the parameters of these giants
It's a tiny fraction.
that is absolutely crushing them on really complex, structured reasoning tasks like advanced Sudoku puzzles, geometric challenges?
That's the perfect hook for today's deep dive. We are looking at the Tiny Recursion Model, or TRM.
TRM? Okay.
Yeah, in this research, it represents a complete paradigm shift. It moves away from relying on just raw scale towards achieving massive efficiency and, critically, generalization through a deeply recurrent structure.
So recursion is the key here.
It's central. TRM is this, well, novel approach.
Yeah.
It's biologically inspired, but they simplified the math quite a bit. It uses recursion within an extremely tiny network.
Just looping back on itself?
Precisely. To progressively refine and improve its answers. Our mission today is really to trace the journey from its complex predecessor model.
There was an earlier one.
Yes, and we'll get into that. All the way to TRM and understand exactly how its sort of engineering simplicity delivered such huge gains.
And it really highlights the Achilles heel of the big guys, doesn't it? I mean, you, the listener, probably know that even when you use sophisticated techniques like chain of thought, OQE,
Or test-time compute, TTC.
right, even with those, the largest LLMs still struggle massively on these structured, hard question-answer problems.
They really do.
Why is that, fundamentally?
Because they generate answers autoregressively. Left to right, one token at a time.
So one mistake early on.
Invalidates the entire chain of logic.
Yeah.
Exactly. One incorrect step, and the whole complex sequence falls apart.
And the benchmarks show this. We know they haven't reached human-level accuracy on the original ARC-AGI benchmark.
Not even close on the harder stuff.
And the sources show that even Gemini 2.5 Pro using really intensive test time compute only hits what? A meager 4.9% test accuracy on the newer, harder ARC-AGI 2 tasks.
4.9% is tiny. And this is precisely the vacuum these tiny recursive models step into.
Okay, so to really get TRM, we need to understand what came before it.
To truly appreciate the TRM revolution, we have to start with its foundation. The hierarchical reasoning model, or HRM. HRM was the first model that really showed the potential of smaller networks on these specific difficult domains. Sudoku, maze pathfinding, and those ARC-AGI challenges.
The places where LLMs were failing.
Consistently failing, yes.
So what was the mechanism? How did HRM simulate that deep thinking with a small model?
It was built on two incredibly complicated but effective core ideas. First, the hierarchical reasoning itself.
Right, the HRM and HRM.
Exactly. HRM used two distinct small networks. The researchers called them 5 low and 5 high.
Which for?
Low and high, essentially. One network ran frequently, the other infrequently. This is based on biological inspiration, supposedly.
Biology. Always complex.
It generated two latent features, a low-level reasoning feature and a higher-level solution feature. That was the idea.
Okay, two networks, two features. And the second key idea?
Deep supervision. This is where the magic of efficiency happened, or was supposed to happen.
How did that work?
Instead of running, say, 384 separate layers, which would be prohibitively memory intensive.
Impossible for a small model.
Right. HRM would take the two latent features generated from the previous recursive step and reuse them as initialization for the next step.
So it's feeding its own output back in.
Essentially, yes.
Yeah.
It was performing the same calculation maybe 16 times over in their setup, simulating great depth up to 384 effective layers without the massive memory cost of one single huge forward pass.
So if you think of it like baking, a really complex cake, deep supervision meant they were taking the same small ingredient, the two-layer network, and recooking it 16 times, refining the flavor, the complexity each time, until they got this rich 384-layer result.
That's a decent analogy. It's elegant conceptually.
But there's always a but.
But the sources make it clear, this elegance came wrapped in some serious theoretical complications. Problems that TRM was specifically built to eradicate.
Right. So HRM was clever, but flawed.
Precisely. That complexity came with, let's say, three key areas of baggage. And the first one was fundamental. The shaky mathematical reliance on the implicit function theorem, or IFT.
IFT. Okay, sounds technical. Why was that a problem here?
Well, to save computational time during training, the HRM researchers used IFT. They combined it with a one-step gradient approximation. It means they justified only backpropagating the error signal through the last two of, say, 6 function valuations in a single step.
Skipping the earlier steps.
Yes. They were making a big assumption that the model had converged to a fixed point in its calculations, that it had essentially settled on the right answer internally.
Ah, so if it's settled, you don't need to worry about the gradients from way back.
That was the hope. They assumed they didn't need to calculate the gradient for every single step before that fixed point.
So they were basically betting their entire training efficiency on this mathematical convenience.
A convenience that, well, simply wasn't holding up in reality.
It wasn't actually converging.
That's the critical finding, pointed out by the TRM researchers. The fundamental concern was that the fixed-point convergence required by IFT was highly unlikely to be reached in practice, especially given the small number of recursions they actually used in the experiments.
So the math was shaky.
The source material shows the calculation was never truly settled. HRM was always, you could say, slightly cheating its way to the result, which introduced enormous instability and compromised the accuracy of the gradients it was learning from.
And that instability must have hurt its ability to generalize, to work on new problems.
Absolutely, which is exactly what we saw in the results.
Okay, that's problem 1, the IFT assumption. What were the other 2 issues TRM had to fix?
The second issue was the, let's call it, biological over-reliance.
The $5 and $5 thing.
Yes. The justification for those 2 networks and the 2 distinct latent variables, which we can functionally call the low-level reasoning feature and the high-level solution feature, it relied on really complex biological arguments.
Making it hard to understand.
Incredibly difficult for engineers to parse why the architecture was effective or how to tune it properly. They had this complicated solution, but without a clear, simple engineering explanation. It felt a bit like black magic.
Got it. And finally, the efficiency paradox. A small model that was actually expensive to train.
Yes, that's the third one. HRM used something called adaptive computational time, ACT, to control how many steps of recursion it took for each problem.
So it could stop early if it solved it quickly.
That was the idea. But this ACT mechanism was implemented using a Q-learning objective, like in reinforcement learning.
Okay.
And that mandated 2 full forward passes through the model per optimization step.
2 passes. Why?
1 to calculate the loss if it decided to stop calculating the halting loss, and 1 to calculate the loss if it decided to continue calculating the continuation loss.
Wow, so it ran the entire calculation twice just to decide whether to stop or keep going.
Essentially, yes. It was incredibly costly. And despite being small, HRM still required 27 million parameters in total. Not tiny.
Okay, so HRM paved the way, but was complex, unstable, and surprisingly expensive to train.
That's the picture.
Okay, here's where we pivot then, to the TRM revolution.
Yes.
The core insight of the tiny recursion model, as you said, was to take that entire complicated, theoretically shaky edifice
And toss it out, pretty much.
TRM achieved massive simplification by using just a single tiny network. How tiny?
Just 2 layers.
Yeah.
It's a remarkable testament to the power of streamlining.
2 layers doing all that work. Wow.
They executed 4 key structural improvements that really drove the generalization gains, and they started by directly tackling that IFT problem.
How? Did they find a better approximation?
No, they abolished the fixed point assumption entirely. Just got rid of it.
So how did they fix the gradient issue without, blowing up their training time?
Instead of using that dodgy one-step gradient approximation, TRM decided to simply backpropagate through the full recursion process.
The whole thing, every step.
The whole thing. That meant backpropagating through all the intermediate calculations, through all the nuddled evaluations of the reasoning part, and the one evaluation of the solution update part.
Wasn't that computationally expensive?
More expensive than the flawed approximation, yes. But it removed the theoretical need for convergence and allowed the model to train using fully accurate gradients. And the result?
What happened?
That change alone was monumental. In one ablation study, just fixing the backpropagation boosted Sudoku extreme accuracy from 56.5% all the way up to 87.4%.
Whoa! A 30% jump just from calculating the gradient correctly?
Yeah. It just shows how flawed that original theoretical compromise really was.
Incredible. Okay, that's simplification number 1. Fix the math. What was number 2? Fixing that confusing hierarchy.
Exactly. They replaced the complicated biological interpretation of the 2 latent variables, the low-level reasoning feature and the high-level solution feature,
With something simpler.
with a much simpler engineering interpretation. They realized one feature, let's call it Diller, was basically tracking the current proposed solution. And the other feature, zero-level dollars to 5, was tracking the latent reasoning state, like the internal scratchpad.
Okay, that makes sense. Solution and reasoning state.
This interpretation immediately answered the fundamental question of why two features seemed optimal. You need a Joller to track the answer you're building, and zero levels to track the process of building it.
And did this simplification help performance?
The source verifies it was essential. They show that using these two features, beat a single-feature approach, which only got 71.9% accuracy, and it also beat a more complex multi-scale feature approach, which hit 77.6%. Simpler was better.
So simplifying the meaning of the parts led to better performance.
Okay.
And the third change, that involved getting rid of one of the networks.
That's right. They consolidated the two separate networks into a single network.
How could one network do both jobs?
They realized the operations were actually pretty similar. Both were essentially updating a feature state. The decision of whether to iterate on the latent reasoning feature zeroer or update the actual solution nailer could be naturally specified.
No.
By whether the input to the network included the original input question, 6L. If 6L is present, it meant keep thinking, iterate on the reasoning vector. If $6 was absent, it meant update the answer, modify the clever.
Clever. A single network could now handle both tasks just based on the input it received.
Exactly. This cut the parameters roughly in half and simultaneously improved Sudoku generalization again. Accuracy went from 82.4% up to 87.4% in that ablation.
Amazing. Less model, better generalization. That's the theme. And finally fixing that expensive ACT mechanism.
Improvement number 4, streamlining ACT. They realized that whole Q-learning objective was, frankly, overkill for deciding when to stop recursing.
So what did they do?
TRM simplified the ACT mechanism by just getting rid of the Q-learning continue loss part. Yeah. That completely eliminated the need for that expensive second forward pass during training.
Did that hurt performance? Usually there's a trade-off.
Surprisingly, no. They maintained generalization performance going from 86.1% to 87.4% in that test, while drastically speeding up the optimization process. That made the Tiny model truly efficient to train.
Wow. So 4 key simplifications. Fix the backprop, clarify the features, merge the networks, and streamline the stopping criteria.
That's the core of the TRM redesign.
What's truly fascinating here, and this feels like it challenges the core dogma of AI research right now.
What's that?
Is that the smaller model size wasn't just a side effect of simplifying things, it was actually a requirement for getting the best performance.
This is a huge finding, yes.
Yeah.
The sources refer to this counterintuitive result that increasing model capacity by adding layers, say, moving from 2 layers to 4 layers.
Which you'd normally think would help.
Actually decreased generalization performance. It made the model worse on unseen problems.
Why does that happen? Because, in standard LLM research, we're constantly told that deeper is always better. Scale, scale, scale.
It points directly to the classic issue of overfitting, especially on small data sets.
Ah, the training data size.
Exactly. These structured reasoning challenges like Sudoku Extreme, they're hard, but they often only have about 1,000 training examples. That's tiny.
Compared to the billions of examples LLMs train on.
Right. So if you give a model too much capacity, too many parameters, or too many layers on such a small data set, it simply memorizes the training examples instead of learning the underlying recursive logic needed to solve the general problem.
It learns the answers, not the method.
Precisely. The finding was that using only 2 layers combined with that deep supervision technique maximized generalization. It proved that the architecture itself, a tiny network iterating deeply successfully, bypassed the overfitting penalty you normally see when trying to build conventionally deeper networks on small data.
So the lesson here for anyone building models on niche or constrained datasets is crystal clear. Don't build a mansion if you only have the blueprint for a small cabin.
Right. Use a small, efficient tool and reuse it deeply. Iterate.
That's really insightful.
Exactly. And they even experimented with a foundational structure within that 2-layer network. For tasks with small, fixed context lengths, like the 9x9 Sudoku grids, they found that an attention-free architecture using only a simple multi-layer perceptron, or MLP.
Just basic feed-forward layers.
Yeah, that worked best. It actually improved accuracy by 10% on Sudoku Extreme compared to using an attention mechanism.
Why would attention fail there? We usually think of attention as being essential for seeing relationships in data.
Attention adds complexity and computational overhead. That can be detrimental when the input structure is already perfectly fixed and small, like a 9x9 grid. The MLP was apparently sufficient to capture the local interactions needed for Sudoku solving without the extra baggage.
Simpler was better, again.
But, and this is important, they found that self-attention, which they call TRM was still absolutely necessary for tasks with larger context lengths and variable input shapes.
Like the maze and ARC tests?
Exactly. Like the 30 by 30 grids used in MazeHard and ARC-AGI. So it confirms the flexibility of the overall recursive approach, but shows that the specific building block inside MLP, or attention, needs to be tailored to the input size and complexity.
Makes sense. You use the right tool for the specific job.
One final piece. A necessary stability technique was integrated. Exponential moving average of the weights, or EMA.
EMA, why was that needed?
Yes. EMA, specifically using a smoothing factor of 0.999, was found to be essential for improving stability during training. It helps prevent the sharp performance collapses that can happen frequently when you train these deeply recurrent networks, especially on small data.
Sort of smooths out the learning process.
It acts like a guardrail. It allowed the deep recursion to work more reliably, leading to higher generalization by preventing the model's weights from diverging too rapidly or falling into bad local minima.
Okay, so we have simplification, the right capacity, the right building block, and a stability mechanism.
That's the TRM package.
So let's bring it all home then and look at the actual performance leap. The numbers are frankly stunning, especially when you compare TRM against the massive LLMs.
They really are. If we look at parameter efficiency first, TRM the version using self-attention for the larger tasks, uses only 7 million parameters.
7 million compared to HRMs.
27 million. So that's nearly a 75% reduction in capacity right there.
Huge reduction. And the performance.
When we look at the hardest benchmarks on Sudoku Extreme, the TRM MLP version achieved 87.4% test accuracy. That absolutely crushes HRM's 55.0%.
Massive jump. What about the mazes?
For MazeHard, TRM it achieved 85.3% versus HRM's 74.5%. Again, a significant improvement.
I mean, 7 million parameters beating these much larger, more complex systems. It fundamentally changes the ROI calculation for building these kinds of structured reasoning systems.
It really does.
And let's reiterate that key comparison on ARC-AGI 2, that newer, harder geometric puzzle set. TRM achieved 7.8% test accuracy. Now, 7.8% sounds low, but
context is everything. That is significantly higher than the 5.0% obtained by the previous HRM model. And critically, it beats the 4.9% accuracy achieved by the massive Google Gemini 2.5 Pro model using extensive search.
So the tiny model is outperforming the giant.
That gap, even though the absolute numbers are small, is crucial. It really shows that for this kind of structured reasoning, the iterative, self-correcting nature of recursion seems superior to the autoregressive, single-pass generation of LLMs.
It learns to think step by step and correct itself.
That seems to be the implication. The core takeaway from the Tiny Recursion model is this. For complex structured reasoning problems, especially with limited data, deep recursion and supervision applied to a simplified tiny network is overwhelmingly more effective than just blindly increasing model capacity or complexity.
It's about the process, not just the size.
Exactly. The massive performance improvements came directly from rigorous simplification and, importantly, removing theoretical compromises that weren't actually practically sound.
It's a huge vindication for thoughtful, iterative design over brute force scaling. It really shows that if you design the computational loop correctly, the reasoning process itself, you can achieve complex feats with surprisingly few parameters.
Well put.
Now, here's the final provocative thought this research raises, something for you, the listener, to explore. TRM and HRM, as they stand now, are supervised learning methods.
Exactly. You give them an input, they provide a single deterministic answer. They find one solution.
But many problems aren't like that.
Right. For these models to evolve beyond just supervised question answering, they would need to somehow extend these efficient recursive methods to generative tasks.
Where there isn't just one right answer.
Precisely. Given that many complex problems can have multiple valid solutions, think of a puzzle with several correct geometric configurations, or maybe multiple ways to solve a maze.
Yeah.
The next logical step seems to be figuring out how to manage that ambiguity. How do you extend this efficient, iterative reasoning to genuine, multi-solution generation?
It makes you wonder what new architectural challenges that generative step would introduce into this otherwise, perfectly streamlined system. Would it break the simplicity?
That's the big question.
Something to think about. Until then, definitely explore this concept of deep recursion further. Fascinating stuff. And we'll catch you on the next deep dive.